We once thought that mantle convection below the tectonic plates could drive plate motions. Early textbooks showed mantle convection cells, like in a beaker of hot liquid on a Bunsen burner, pushing plates along from below. Current dynamic models have plates moving as part of a gravity-driven convection system that pushes young hot plates away from spreading ridges and pulls old cold plates down into subduction zones. Remember that lithospheric plates, also called tectonic plates, have a layer of crust on top of lithospheric mantle, the outermost rigid part of the mantle. These move as a single unit. The hotter asthenosphere beneath the plates is solid but less rigid mantle rock that can slowly flow. Now let's look at the broader picture. This map shows how the seafloor increases in age with distance away from spreading ridges, such as the East Pacific Rise or the Mid-Atlantic Ridge, where new ocean plate is forming. Spreading ridges stand 2,500 meters higher than deep ocean basins. At a spreading ridge, the ocean depth is only about 3,000 meters. Ocean depth increases with age of the underlying plate, so that where the plate is more than 80 million years old, the overlying ocean increases to 5,500 meters deep. Let's examine the formation of new oceanic plate and how that plate cools with age. As hot mantle rock rises to lower pressure, a small portion of this upwelling asthenosphere melts to form magma that builds the 7-kilometer thick oceanic crust at the edges of two diverging plates along the ridge axis. Beneath the crust at the spreading ridge, there is only a thin layer of lithospheric mantle because it is unusually hot in the upwelling zone. This hot, and therefore lower density mantle rock, supports the 2,500 meter elevation of the spreading ridge. As the plate slowly moves away from the ridge, it cools by conducting heat through the crust to the cold ocean water above. At the same time, the underlying asthenosphere cools and adds to the bottom of the lithospheric plate. Thus, although the crust maintains its thickness during migration away from the ridge, the lithospheric plate thickens and cools to create ocean basins that extend 5 kilometers in depth. A simple way to think about elevation is that the plate is young, hot, and high at the spreading ridge and becomes old, cold, and low during the aging and cooling process. Mathematical modeling of this cooling process illustrates the ocean plate becoming cooler and thicker with age. The temperature at the bottom of the plate is about 1,300 degrees centigrade. Notice that most of the cooling process occurs between age 0 at the ridge and about 80 million years when the ocean plate has grown to about 100 kilometers thick. The upper plate is less than 600 degrees centigrade, thus is the only part of the plate cold and brittle enough to fracture and produce earthquakes. Though still rigid, the lower plate is warmer and can deform in a ductile or plastic fashion. So what force pushes oceanic plates away from spreading ridges? Any mass on a slope is affected by gravity, seen most dramatically with avalanches and landslides. Spreading ridges are broad undersea mountain ranges, and although the flanks of a spreading ridge are a relatively gentle slope, the mass on that slope is humongous. The force of ridge push is 0 at the ridge, but increases quickly with distance and age, pushing the cooling and thickening oceanic plate away from the ridge. Now what about slab pull? We will consider a 30 million year old oceanic plate, which we'll call a slab, subducting at 5 centimeters per year into hotter asthenospheric mantle beneath a continental plate. As the oceanic plate subducts, the warming process takes many millions of years as the slab descends. The deeper part of it is continuously replaced in a conveyor belt fashion by a cooler plate from above. Mathematical modeling again illustrates the temperatures within the subducting oceanic plate. In this example, lithospheric mantle rock in the subducting plate at 150 kilometers depth is 1,000 degrees cooler than the asthenospheric mantle at the same depth. The cooler temperatures mean that the density of rocks in the subducting slab is greater than the density of the hotter asthenosphere. While gravity pulls down on all rocks, it pulls down harder on more dense rocks. This enhanced gravitational force on the cooler and denser rocks in the subducting plate is the slab pull gravity force. Earthquakes, including great megathrust earthquakes, occur on the shallow part of the boundary between the converging plates and within the shallow parts of both plates near that boundary. In addition, there is a zone of rock cooler than 600 degrees Celsius within the subducting plate that remains brittle and within which earthquakes can occur to depths of hundreds of kilometers. Observations of intraplate earthquakes and other indications of stress with tectonic plates suggest that the slab pull force is usually larger than the ridge push force. It is noteworthy that fast-moving plates, like the Pacific Plate, generally have a fast spreading ridge pushing on one side while the subduction zone pulls on the other side. In this big picture view, we see that lithospheric plates are part of a planetary scale thermal convection system. The energy source for plate tectonics is Earth's internal heat, while the forces moving the plates are the ridge push and slab pull gravity forces.